So let's see, Randy, you didn't write on your test, did you? Can I borrow that blank test?
Do you need mine?
If you're not, oh, you wrote it in the other one?
Yeah.
Yeah, I don't have any extra tests. I got it. We're good. I'll give it back. I just need something to go off of when we're solving this. All right. So let's go through the test. Let's see what's grade breakdowns were. They were all over the place. I think the high grade. Well, there were hundreds. Low grade was either 22 or 15. I don't remember which class this is, but there were some 20s, there was some hundreds, there was a bunch of crap everywhere in between. So kind of all over the place.
So we all suck.
Well, you know, the class average was, I think, a 71.
So we still suck.
Well, that's average. That's right around a 70 is kind of where exam averages probably should be. So I would say the average for the exam was about probably where it should be, but very few people got a 71. It was either
You want to take 3 points off?
Extreme higher or extreme lower. So if you're anywhere in the mid 70s, you were definitely an anomaly, even though that's about the average of the class. All right, so let's look at this. All right, midterm solution. Okay, so we have this list for number 1. So 1, 2, 3, 4, 5, 6. Like that? Does that look right? All right, and we were supposed to extract the 6 from this, right? All right, so if I were writing this, I'd actually probably draw some lines. I'm going to try to do this with a little tool here. So let me do... Arrange, send to back.
By the way, all the cookies were laced with meth.
All right, so this is the entire list here, right? Shut up! So this is the entire list here. Well, what's going to be the best way? Well, hell, let's just do it this way. Let's just write the individual pieces. If I had a piece of paper I was writing this, I would do it kind of by hand and draw. Well, actually, I can do it up here. Here, we'll do that. Because it's easier to diagram these that way. So we have 1, 2,
You could just lift
3.
the screen and do it right under it.
Then we have what? Is there another list now? Oh, yeah, here. 4. And 5. And 6. Like this? All right, so I like kind of drawing out when you need to do cars and cutters, I kind of like diagramming it. So this is actually bucket 0. This is bucket 1. This is bucket 2. Okay, so some of you did this with cars and cutters. Some of you did this with list refs. Didn't matter. Whatever made you happy is fine. I think I just said write the necessary code to pull this off, right? So this would be list ref. So if this guy is called LST, let's say. So some of you said, you put this into a variable called LST. So if I said list ref LST2, that would give me this piece right here, correct? What I have highlighted here. Okay, so this is 0, this is 1, this is 2. So if I say list ref, this is going to get interesting. Let me say LR for list refs, if you'll let me. It's all the way down there, so it fits. So this is LR for our list. I can make it closer. All right, then we're going to take LR of that guy at bucket 2. So now we've extracted just this piece. This is bucket 0. This is bucket 1. So we're going to take LR of that guy at bucket 1, and then we're going to take the car. That'll do it. You could have certainly taken the same approach to do all the cars and gooders and all that jazz. But in any case, punchline is break it down like this. Draw your little lines and that kind of stuff, and life would have been a lot easier. This one was missed pretty often, and not a real hard problem, actually. Just a tedious problem, but hopefully you see that. Questions about this one? All right. And to be honest, I'm not even sure that that's their answer, but I think it works. I'm pretty sure that works. We've already established that I might not be able to solve this exam. All right. Nah, I'll be all right. Number 2, write a predicate called is even that takes a number as a parameter, returns true if it is an even, if it is even, and false if it is odd. So let's go over to have a blank Dr. Racket here. So we'll define blah, blah, blah. Is it case sensitive? I don't know. I don't think it would have worked, but it is case sensitive, so I'm guessing it would not have worked. So define as even to be a lambda that takes a number as a parameter, and this guy is going to just return mod num2. Well, I said it should be true if it's even, false if it's not. So mod num2, and then we'll say equal to 0. That guy. So we'll take num in. We're going to take num, divide it by 2, give us the remainder. If that's equal to 0, this will return true. If it's equal to something other than 0, in this case, the only other option would be 1. It would return false. So that's number 2. Predicate for is even. Questions on that one? Number 3, write a procedure called Fizzbuzz that takes a number as a parameter, returns Fizzbuzz if the number is evenly divisible by 3 and 5, Fizz if it's evenly divisible by 3, Buzz if it's evenly divisible by 5, and the number itself otherwise. So we'll say define. Not even close.
Feel okay over there?
Define Fizzbuzz.
Do you need a cookie?
To be lambda, we'll have this guy take in a num, and then we're going to go ahead and create a cond, and we're going to say and num mod num3 equal to 0. And mod 5 equal to 0. If both of those things are true, then we're going to boil down to Fizzbuzz. All right. Otherwise, just this guy. This is Fizz. This is Buzz, else num. Like that. So we'll take a number in as a parameter. If that number is both evenly divisible by 3 and evenly divisible by 5, boil down to Fizzbuzz. Otherwise, if it's evenly divisible by 3, boil down to Fizz. If it's evenly divisible by 5, boil down to Buzz. Otherwise, boil down to num. Make sense? Oh, is there not a mod function? Is it just percent?
It's modulo.
Modulo?
Yeah.
Oh. And you will notice I didn't take off any points if you guys put a percent symbol in or something like that.
Is the percent symbol not actually working?
I might. I don't know.
It does not.
Nope. So, this guy right here. So if I were to say Fizzbuzz of 5, that gives me buzz. Type in all the other things, that should work fine. All right, questions on that one? All right, so that was number 3. Number 4, write a lambda calculus expression where a variable x occurs free and a variable y occurs both free and bound. Okay, so x is free, y occurs both free and bound. Is that it? All right, so we'll create an app expression. The first thing in it will be a lambda. We say lambda a, and is x supposed to be free? Where x occurs free and y occurs free and bound. Okay, so here's an example here where x and y both occur free. And then the second part we can say lambda y, like that. So this is an app expression. First part of it is a lambda, takes in whatever you want to take in here, as long as it's not x or y. And then here x and y both occur, and they both occur free because they're not bound by this variable environment there. And then in the second part of our app expression, we take in a y, and y occurs, so y occurs bound by this declaration right here.
Could you also do...
you could do a whole bunch of stuff.
Y, then parenthesis lambda, y occurring bound, and then x, y.
So you want to just do this, so y, and then the lambda.
Y occurring bound there, that portion, and then
X, Y, something like that. That's fine. I mean, you could literally you could sit here for a month and keep coming up with examples of...
If I do that, can I get the point?
No. All right, so questions on that one? All right, let's see. Next one. Convert 1321 from base 8 to base 16. Oh, I love these. All right. It's the same thing. Okay, so 1321 is currently in base 8, right? And I want you to convert it into base 16. So the very first thing you should do is let's go ahead and convert it from base 8 into base 10. Okay, so 1, 3, 2, 1. The 1 is in which place? This is the 1's place. 8's place. 64's place. What's 64 times 8? 512. All right, so this is 512 plus 64 times 3, which is 192, plus 2 times 8, which is 16, plus 1, so 512 plus 192 plus 16 plus 1 is 721. So that's 721 in base 10. Sound right? All right, so now we need to convert 721 from base 10 to base 16. So we're going to take 721, we're going to divide it by 16 over and over again. So 721 divided by 16 gives us 45 here. 45 times 16 is 720, so it's remainder 1. 45 divided by 16 would be 2, 2.8, so that gives us 2 here. 2 times 16 is 32, so this is remainder 13. Right, 32, 42, okay. And then 2 divided by 16 goes in 0 times. 0 times, this is remainder 2. So then we read, since we have a 0, we read it from bottom up. So the answer is 2. And then what does 13 map to in hex? And then 1. So 2d1. That look right? All right, so that is number 5. Questions on that one?
apparently I could not add that there.
Oh, good. Yeah.
If you move the places of the ones and you back to decimal, but the decimal that we would add, you got 2 decimal places. So 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 you got 2 decimal say 16, right?
What's this?
I forgot the ones place and when I went to decimal, so I had 8 on 5, right?
Oh, I got you. So you were just off by a little bit?
Yeah.
That's fine. Show it to me at the end. If you deserve points back, I'll give them back. Yeah, so at the end, if you think I graded something wrong, just let me know, and I'll tell you whether or not I think you're out of your mind or not. If you think I gave you too many points on something, let me know as well, because I should redistribute those points to people that actually earned them, right? All right, so this was, what number did we just do? 5. Okay, we just did 5. 6, what is a grammar? What is a production? Let's get rid of this. Grammar is a set of, you could say formal rules or something like that, but a set of rules for defining a language. A production, an individual rule. Individual rule within a grammar. Make sense? So if you look at the next little step there, the given bin tree thing, the grammar is bin tree, and then you have 2 productions in there. The first production is just an int. The second production is symbol, a list containing a symbol followed by a bin tree followed by a bin tree. Okay? I don't know if I had too much caffeine. Look at that. Well, I always have the shakes, but it feels like my whole arm is shaking. All right, well.
Do you need me to rub it?
I do. All right, Joel, if I go down, you take over. Don't drink my coffee. All right. Number 7, write an example of a bin tree that contains 5 numbers. Okay, so we're going to use this grammar up here, so let's go ahead and just create ourselves another slide here and put that grammar at the top. So a bin tree, is it 1 equal sign? What? How would I write it? Oh, two, blah. Okay. Are you crying?
The doctor moved my shoulder in not fun ways.
You got to make sure his work is structurally sound. Like when you build like a wall or somebody, you got to bang on it a couple times, make sure it's good.
Don't do that to your boat.
Champagne bottle. All right.
You tried that on your boat. Look what happened.
That's true. All right. So we have int. Man, look at that. Can't even barely read it. All right. So we have int or symbol bin tree. Okay.
Just means it's time for my
Symbol bin tree. That's weird. You can't make that smaller? Oh, whatever. All right.
That's what she said.
So many things I get recorded from you, and YouTube keeps flagging it. I keep putting. That's why I keep having those adult commercials that show up in my advertisements.
You seriously had that?
That or like I think I have an advertisement for Depends.
You serious?
Yeah. Probably because of all the diarrhea words. Every time you say diarrhea on recording, it's like one more check mark in the column for adult diapers.
The more you say diapers, the more
So good.
This one definitely is going to have its pencil.
Maybe they just somebody saw you on it and just figured you might.
Well, they don't make my size. Yeah, no, I pretty much have to go to like Target and buy whatever the smallest tent is.
Just get a tarp. Well, sleeping bag looks better. It'll absorb.
Really? I would think a tent would be way better because you can just hose it out.
Sleeping bag. Just go
Oh,
to
this is just recorded.
go to laundry, man.
Was this on the exam? This was not on the exam. All right. So let's see. Write an example of a bin tree that contains 5 numbers. Did I say at least 5 or did I say exactly 5? All right, whatever. All right. So we're going to have let's say A. Okay, and then so we're going to have a list contained by followed by two bin trees. So the first bin tree we're going to have B. Second bin tree we'll have a C. We're going to put some stuff in those. All right, and then we got to finish our list there. So now we have 3. So we'll say D2, C3. Well, actually, hold on, I need to go. In order to get the actual numbers, we actually need to go deeper. You like that? All right. Well, so let's start off with an example of a simple bin tree. So we can say A followed by B2, C3. All right. That would follow the rules of a bin tree. So we have a tree symbol followed by bin tree, bin tree. Oh, actually, here we have another guy. So this is, let's say 4, 5 here. So first production is just an int. So here's a bin tree. Here's a bin tree that follows our first production. Here's a bin tree. Here's a bin tree that follows our second production. So here's a bin tree. This is a bin tree. This is a bin tree. All right, so now we have 4 numbers. All right, so actually this is a harder question I thought I was going to ask. Because I remember thinking about saying at least 5. Because getting exactly 5 is actually going to be tough. All right, so we have exactly 4 right now, right? So then what we can do here is we can say,
Put the C into the B where the 3 is. Yeah, that's all we did is just do like A1.
I got you. So you did this. You did C3, 4 here,
And then, like
and then
5 on
D.
that. You're one out.
Can you just get rid of the D and just make it?
Get rid of
No,
the D.
you gotta have the D.
So we have 3 numbers there. Relax, relax.
But then you need the second part of the.
This guy right here.
And then you can put just like a random whatever on there.
So we can put like 1, 2, right?
Yeah.
So these are 2. This is a tree. This is a tree. But these guys actually aren't part of this guy, right? So this is the tree associated with B here. And then this guy would be like a 7. So like that. So here's our outer tree. So that's a symbol followed by a tree and a tree. So there's our first number 1. Here's our another tree. So there's a tree followed by, that's our symbol, followed by a tree and a tree. Each of these trees is a symbol followed by a tree and a tree and a tree and a tree. So there's our 5 numbers. But I'm pretty sure that if you did more than 5, I also gave you credit. Because my intention wasn't necessarily to make it so that you came up with something and gave exactly 5, but that you kind of knew how to put trees together. Okay, questions on that one? All right. 8, write a procedure called SumTree that takes a bin tree as a parameter and returns the sum of all the numbers in the tree. Okay, well we can test on this one. So what should the sum of this guy be? 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Should we choose 17 for this guy? All right. So let's go ahead and give myself a define tree to be equal to this guy. Do these have to be quoted? Nope, we're good. All right. So that's what so we're saying this is a tree definition, right? All right. So we call this guy SumTree. So we'll define SumTree to be a lambda. Lambda that takes a tree as a parameter. And now we're going to go through and we're going to parse through this tree. Now we know we're always either dealing with the number or we're dealing with the list. Correct? Okay. So Very first time we're looking at the tree that looks like this, so we ask ourselves, is this a list? If it is a list, then what do? We know the first element will be a symbol, so we can assume it's a legal tree. So then we can kind of burn past that because we're not dealing with symbols here, right? Okay, we're not interested in symbols in this solution. So we can ask the question, we'll say, cond list tree. If it's a list, then what are we going to do? We're going to go ahead and peel off the car, and we want to get the car of the cooter and the car of the cooter. The two sublists of this guy, the subtrees of this guy. All right, so if we have that, then what are we going to do? We're going to add some tree of the catter of tree. So that should give us this piece. Okay, that's the car of the cooter, as well as the car of the cooter. CADDR tree. So we'll add those two guys together. Make sense? So call some tree on this piece, call some tree on that piece. Okay? So that's if we see a list. Else, if it's just the number, what are we going to do? Boil down to that number. Specs, how many arguments? Oh, I didn't put my extra parentheses in there. Very nice. Some tree of this guy. All right, so that's what we do if it's a list. This is what we do if it's not a list. No, I know. Some tree, lambda, tree, cond. If it's a list, do this stuff. So we're going to call some tree here. We're going to call some tree right here. We're going to add those two guys together. Oh, one extra one there. Yep. There we go. So now we should be able to say some tree of tree and get our 17. So as long as you were close on the parentheses, that's fine. This is the rough structural logic you were looking for. So, taking a tree, we only care about when it's a, well, if you see it's a number, just return the number. Otherwise, peel off the symbol and do the sum on the trees. All right, question on that one. All right, so now we're at number 10, right? No. Number 9, what is the purpose of storing lambda expressions in our variable environment? Well, so that we can support named functions. So up to this point, we can store name-value pairs where we have a variable name associated with a value, where a value is always like a number or a symbol, right? Well, now we can store functions. So just like in Java, when we have a function, if we need to be able to call upon that function later on, we need to have a name to call it by, right? So we have to store that function with a given name somewhere. So what's the purpose of storing lambda expressions inside of our variable environment? Well, because lambda expressions represent functions, it gives us the ability to store functions and use them later. Otherwise, if we didn't have a name, we'd have no way of accessing them later. Make sense? All sorts of interesting, crappy answers to that question. All right, now number 2 questions on that one. Number 10, write a procedure called apply GD that takes a list of positive numbers as a parameter and returns a new list of the same length with every number replaced by the largest integer value that evenly divides it. Okay, so right off the bat, we should be thinking about map here. We should also be reminded that map has the limitation that it only allows us to map functions with one parameter across a list of things. All right, so we're going to break this into little pieces. First piece we're going to write here is, how do I write a function that takes in a number and tells me what the greatest divisor of that number is that isn't itself? Start with just that function. All right, forget about map, forget about all this other stuff, just this one function. So we're going to create a function here. Define GD to be a lambda that takes in a num. All right, and this guy's job is going to be to return the largest value less than num that evenly divides num. Make sense? Okay, so how are we going to do that? Well, let's say we had a 6. Well, right off the bat, if we say num divided by num and see that the remainder is 0, we can't just return num, because that means every value would evenly divide itself, and then we would have Levi's solution. Okay? Levi's proposed solution. Levi's proposed solution. All right, so what we need to do is we probably need to have a value that's 1 smaller than this, right? Okay, so we're going to have num. Let's actually just write a second function here real quick. Define GD helper. And this guy will be a lambda that takes in a num and a cur being the cur highest value. And we're going to say if, you say modulo, num cur is equal to 0, if that's a true statement, boil down to cur. All right, let's kick it down the line. Else, we'll call GD helper, passing it the same num and passing it cur minus 1. All right, so that's our GD helper. So then what's GD going to do? It's going to call GD helper, passing it num and num minus 1. Make sense? So let's go ahead and test this piece real quick just so we can see it work. So I should be able to pass any number into GD, and it should spit out the number, the greatest number that evenly divides it. We know that once we get to 1, we're fine. And I think I said they're positive numbers, right?
Yeah.
All right, good. Covered my butt. All right, so let's go ahead and run this here. So we're going to say GD of 6 should give us a what? Ruh-roh. Oh, I did my usual thing. Parenthesis diarrhea. All right, there's that guy, that guy, that guy, that guy. GD 6. There's our 3. GD of 4 should give us a 2.
4028.
GD of 5 should give us a 1. 4028, you said? Of course, that's the correct answer. Okay. All right. So GD seems to work. I happen to have a function that takes in 1 parameter. What's the name of this guy supposed to be? Apply GD. Okay. So now that we have all the tools that we need for map, define apply GD to be a lambda that takes in a list of numbers. And what are we going to do? We're going to map GD across list of numbers.
Wow, you're really good. Apply GP, GC.
Oh, really? Yeah. I told you, I've got the shakes today. All right. Apply GD, a lambda, list of numbers, and we're going to map whoa, did you see that one? GD across list of numbers. All right, did I give you an example you should try it on or no? Okay, no. So let's go ahead and just give ourselves an example. So we'll do apply GD. Actually, let's define it so we can look at both of them. So define L to be 1, 2, 3, 4, 5, 6, 7. And 4,028. All right. So there's our list. And then we want to go ahead and say apply GD. Man, something's not kicking right here.
Other hand completely.
I know, but it's something like
the shakes.
yeah, I know. Something just feels off though. I'm like foggy. I told you, Joel's going to be taking over here pretty soon. If I go down, just kind of shove me over to the side.
Too much fun in Colorado? Catching up on
Colorado
that?
drops in the top.
All right. So, what should our answer be here? Oh, here we'll go ahead and just print out L2. So we'll get both of those. So we should get this list displayed first, and then we should get a 1, a 1,
No, that's gonna mess up. The one's gonna mess up.
one's
Divide 1 by 0.
one's gonna break it.
Yeah.
Oh, that's right. I said in class you could exclude 1, right? All right. So we'll just take the 1 off. All right, so we should get a 1, a 1, a 2, a 1, a 3, a 1, and then what, a 2014?
Yeah.
So right there. All right, that's number 10. Passed. Did I pass? I passed. Oh, that's not true. There were several 100s on the exam. There was lots of A's.
And then there's only 8 of us that are idiots?
Well, I don't remember. But I can't bring up the statistics right now without showing you everybody's grades. I'd have to stop the recording. Actually, no, hold on. Ooh, no, that was not going to work. It's still be on the recording. See, that was almost.
Can you pause the recording?
I think you can, but I've never tried it before.
Pause.
There's a pause button.
Oh, yeah.
Are we playing with fire here?
Alright.
Seems to be still cooking. So I guess we have to give that a second to cool off before we can start back up. Okay, so
Couldn't you just unplug that?
that would have broke the recording.
Looks like it's all
Really?
looks
Yeah.
like it's all the way off now.
Yeah, it because the screen resolution changes size. That definitely breaks it.
There it goes.
Promise. Ask me every now and then. I'll bump that, and we got to start over. Okay, so it should be popping up here in a second. So 20 exams. Minimum value was a 22. Maximum value was a 100. Average was a 70.15. There were 6 grades, 90 to 100, 3, 80 to an 89, 4, 70 to a 79. So 13 people did C or better. And then notice there were no D's, no high F's. Okay, so we kind of resumed scores in the 40s. All right, so yeah, so basically it's a pretty clear separation here. We have those folks that pretty much know what's going on.
Hey, I was
Okay.
on serious narcotics that day. Don't judge me.
Would it really have mattered?
Probably.
All
I got super sick during the exam.
right, so here's folks that generally know what's going on, and here's folks that either need to catch up. They got to see where they're remedial. We had 2 different scores in the 20s, and then we have one person taking the exam right now that will very likely be at least that low.
Oh my god!
Wow.
I didn't say the name.
He's not recording, but the best part is he's not going to watch the video.
I haven't divulged any information. I didn't say the student's name.
Who's it? Not even-
Don't say it. All right. So in any case, for the folks that got the below a 50% on this, you're obviously not completely screwed, since I have the policy where if you do well on the final exam, I'll replace your midterm with whatever you get on the final. But obviously, there should be a wake-up call that there's some remedial issues here. So while it may have been difficult to get in the 90 or above mark, I mean, the exam wasn't a trivial exam, but I do think the exam was pretty fair. I don't think it was like overly impossible. So maybe this was obviously people who are doing very well. I think this group of people right here are much more indicative of probably how everybody should have done. So probably low 70s to mid 80s is, if you are anywhere in that ballpark, I would say you're in pretty decent shape. You know, I've been saying it all semester, and I said it last semester, this is pretty much our hardest class. All right, it's not easy stuff. So this one or compiler is what you'll have with me next semester. So you get a whole year of this. Okay. this nightmare is going to continue. Okay,
You have 2 cats, right?
Yes, I do have 2 cats, but one of them is immortal, so, you know.
One
And the other one's really quick, so.
It's okay.
Wait, I thought you said Gracie.
Gracie can catch Sissy.
So, isn't Gracie
Gracie's immortal, yes.
So,
But just because Gracie can catch Sissy doesn't mean anybody else can.
Trust me.
But it is funny to see her run down Sissy. Because when Gracie,
on video, I want to see.
well, I mean, you can't, you don't have the video ready, right? We'll be sitting there watching TV, all of a sudden they just come as a tear through the living room. Because Gracie knocks over that cat tree in the living room. So she chases Sissy up there, and she climbs halfway up the thing, and then it falls over because she's butt heavy. She pulls the thing down.
Does she like catnip?
Gracie? Oh, all cats like catnip.
Good, I'll wrap some, rat poison.
Rat poison. Gracie's pretty discerning. Like right now, she's on probiotics to help her with her, she's mostly fixed now. It seems like her diarrhea has solidified. Well, she was on antibiotics for 2.5 months. So it killed
the worst part of the situation.
Well, it killed off all of the bacteria, all the good and bad bacteria that was in her body. So she didn't have any of the good bacteria in her stomach to help her digest correctly. So now she's back to normal there, but we've been having to give her probiotics. But now she's become highly suspicious of any food you put in front of her. Because she pretty much just assumes you're lacing it with something.
And it's not something.
Yeah, you're lacing it with something. So, yeah, but yeah, she's about as good as she's going to get probably. She did lose some weight in it, so frankly, she looks cleaner than she's been in a while because I think now she can reach. So there are some perks. You got to leave in 1 minute.
0 minutes.
0 minutes. Get out. All right. So. All right. So that's the scoop with the exam. We're going to talk here for at least a few more minutes, kind of see what's going up next. I might not go the whole time because I do want to give people a few minutes to come up and ask questions about their exam, and I have to go pretty quickly right after class. So I got a tea time, and it gets dark very early. Huh?
Where is it today?
Oh, it's Mequon Park,
The gun range?
the gun range. Yeah, did everybody in here hear that I almost got shot? Was it?
What?
What?
Are you going fishing?
Yeah, everybody heard.
So
Yeah.
mad that you didn't think
Oh yeah, you weren't here yesterday. You didn't hear that.
none of it.
Yeah, so I was golfing at Black Wolf Run, kind of a famous golf course up in Sheboygan on Sunday, and we had to go late season because we had these coupons that allowed us to play this $275 course for $30. So they basically, after the course is all but closed, we're allowed to play it with the steerage. We're out there, and apparently there's like a hunt lodge next door. I don't know if it's part of the Kohler American Club thing or if it's just a separate hunt lodge. But the whole time we're playing the front nine, we keep hearing gunshots. So we get to the 8th hole, and we're standing there, and we kind of see the hunters out there. We see the guys in the orange and their dogs and stuff like that. And all of a sudden, the number 8th hole, the sign explodes. Okay? They shot the sign. And it all kind of happened so quickly. We saw the dog kind of sort of running towards us, and then the dog, I guess, chases the bird up into the air, right? Is that the thing? So, and then the hunters, they're following their dog, and then they go up. And before, I guess, he noticed that I'm aiming at golfers, he pulls the trigger. And the sign, so I'm guessing it's hard to say because I was on like an elevated tee, so it's difficult to say how far I actually was from them. Somewhere between... It had to be at least 100 yards. So 100 to 250 yards would be my guess, just guesstimating. They weren't like standing right next to us, but they were close. We could see details on the dog and stuff. Huh?
Julie's yell at them.
Well, so we're standing, we weren't even in a condition to yell. We were kind of like ducking for cover. And then the guy just kind of waved like it was no big deal. Like, oops, sorry. You just shot at
Sorry,
us.
we almost killed you.
Sorry, my golf ball kind of went by you.
Well, no, it gets even worse because afterwards I tried to say something to the people in the clubhouse. They acted like it was no big deal. We almost got shot on your course.
I sent you a picture. You should look at it. It's pretty good. Oh, if it's separate.
All right. So let's talk about what's coming up next. Put ourselves in that mindset. We still do need to finish debugging the code for getting the thing into our variable environment. But before we do that, let me go here. And we're probably going to do that next time because I want to get that done and not just work on it for 5-10 minutes and then call it quits. So, since okay, so let's look at what's coming up here. Let's get down to where we left off. Okay, so this is kind of in the area where we're at right now. We have our lambda calculus expression. We have a little bit more complex version of this. We've already written the one that has more than one parameter. 0 more parameters, right? This guy?
Sure.
Yeah, we have it as a list. All right, so we're already doing this stuff, and then we have our app expression, and we also have added a lit expression in here as opposed to not just var expressions. So we've dealt with literals. Playing Hearthstone. It's like, see, this class is so easy. I just play video games during it.
We haven't anything.
All right. So we're going to start evolving our language into a language of expression. So at this point, we've been thinking about things in terms of lambda calculus expressions, which aren't that useful for us. They're our way of representing things. We've been talking about constructors and things like that. And if you remember back to some other courses, I've talked about things like JSON and XML as data representation languages. So we kind of given ourselves some tools for representing our data, but we really can't do anything with it yet. So we need to start having expressions that we can use to operate on these guys. And this is going to come into several different categories. We're going to have types to determine what kind of thing is and are we allowed to do something on it. So we have this constructor called value of. So this is value of an expression given an input. What's it going to resolve to? So this starts showing us kind of where what we have now kind of fits into the world of interpreters. So now kind of understand that this one picture right here kind of shows this class and next semester's class at the same time. So what we're doing in here is this top one, execution via an interpreter. So you're going to have some sort of front end, some way for the user to get their expressions into the interpreter. Okay, right now what do? We type it into schemes. We write all this code here, and then at the very bottom we actually, try to call our run program and stuff like that. That's how we get it into our code now. But in real life, we probably have either a program where it reads in from a file and does all the stuff we tell it to do, or maybe if we think about it like our terminal and in DOS, this is an interpreter. So when I type in ls and press enter, it does what it means for ls. Okay? All right, so we have to have some way of getting information into the interpreter, and then from there it goes through something called a syntax tree. Okay, what do we call our syntax tree? How do we produce our syntax tree in our interpreter? What's that called? Parse expression. Okay, so we have parse, and parse turns our code that we've put in into a collection into a representation that is digestible by the interpreter. Okay, then the interpreter goes and does its thing. Okay, and that's what we're in the middle of doing right now, but still we're building up abilities. So our interpreter knows how to do a whole bunch of individual things, but what it sucks at right now is putting those things together, right? We have a variable environment, but we really can't use it for anything. Okay, we know how to have functions, and soon we're going to be able to store those in our variable environment. Well, we really don't know how to apply them to anything. Why? Because I don't have anything to do. We don't have math expressions. So I can have a literal 5 and a literal 6 and say I want to add these two guys together, and that's all fine and dandy, but we don't know how to add. Okay, we don't have abilities inside of our language to actually do things. We just have abilities to represent things. So kind of foreshadowing where we're going with this is we're going to start being able to do things with our language. So our language is going to evolve in the second half of the semester by having the core that we've already built and then being able to actually do things with it to the point that we're going to be able to write full logic-based applications, seeing that we have we'll have a real programming language. Okay? As opposed to what are we going to do next semester? Next semester, you notice the first parts are exactly the same. You have your front end, so you're going to get your information into the language in the exact same way, whether it's typing it directly in, reading from a file, whatever it is. We're still going to generate a syntax tree, so there's still a need for this data representation. We're going to take what you typed it in and we're going to convert it into a format that we can work with. All right, so whether we're working with an interpreted language or a compiled language, we have to do that in both of those cases. All right, but now with our interpreter, we just handle it right then and there. With our compiler, what do? We further represent our data. So the syntax tree is actually an intermediate representation of our information. Once we feed it through the compiler, and what's the job of a compiler? High level to a low level? Yep, so it's going to convert whatever our syntax tree is, which is at the very least going to be a higher level representation. So right now we can think about our syntax tree as looking like the output of parse expression. So at the very least it's going to convert that into something that's much, much, much more verbose. Something that translates to a one-to-one setup with the CPU. Okay, so our CPU knows how to do a whole bunch of individual things. So the difference here is that our interpreter, okay, in a compiled language has already been written for us. It's called the machine, right? So our CPU already knows. No, not with that test score. All right. What's that saying?
I beat him by 1, so.
He's like the most underachieving smart kid I know. Well, at least top 3. Right? Well,
I can't be top 1 because that means I'm achieving at that. So I kind of underachieve.
Exactly. See, even that was an intelligent humor. Okay, that was intelligent humor right there. And I mean, man, he could be so much better than he is, but he's just not. You know what I'm saying, Joel? All right. So at the end of the day, we need that compiler because we already have this hard-coded interpreter that is a CPU, right? Okay. So we need to have that compiler that can translate whatever data representation language we agreed upon over here into, hey, this is what you got. You put an Intel CPU into your machine. This is what he knows how to do. Deal. Okay. So you're going to have to convert it into stuff he understands. All right, so that's where that compiler comes in. So you got to think about the job of a compiler is pretty complex. The only reason I think that class is easier than this class is because in the compiler class, we use languages that you're already more familiar with. So we go back to, I actually probably use C in there to scare the crap out of you, but C or C++, but it'll feel less foreign than Scheme. Plus, I need to knock the recursion out of you because already some of you are having trouble writing things iteratively, which is good because that's kind of what I suggested might happen. As you get so far into Scheme and doing everything recursively, all of a sudden recursion becomes your go-to move for everything, and you realize that you're now no longer able to write for loops. It's like, wouldn't we just do this recursively? You got the weird twitch thing going on. Okay. So that's kind of in context of where we're going, where we're going to be building in this front end, plus kind of further extending our interpreter and really almost blurring the lines between what is the interpreter and what is the API that sits on top of it. Okay? So when we think about programming languages today, so let's just use something that we're all comfortable with, like Java. Okay? The core Java language lives where? In terms of the Java language itself, it lives inside of java.lang, right? So java.lang has the default, this is what Java is stuff. Without importing anything extra, I have access to this crap. Okay, so we can call that the programming language. That's the Java programming language. Then outside of that, we have a whole bunch of stuff that we can pile on top of that. So like, for instance, java.util. That's where our random class came from. That's where the scanner is, things like that. Okay, this has other things in it that aren't mandatory for the language. These are power tools that allow us to accomplish extra stuff. Okay, similarly, we have java.io. Okay, again, it's going to make perfect sense that we might want to read things in from files, read things in from the user. We might want to do input and output, right? But again, it's not mandatory for this thing being a programming language. Pretty useful for us to do anything, requiring any sort of I/O, but not mandatory. We certainly could implement all the stuff from java.io in terms of the stuff that's in java.lang. Life wouldn't be very convenient, but we can certainly do it. Okay? So when you think about a programming language, our modern languages, they're like layers of things. Okay? And at the core of it is what we want to think about as being our interpreter. So we're going to have an interpreter that isn't going to end up doing as much stuff as java.lang does, but it's going to do enough that we feel like we can write little tiny programs. For instance, maybe in the end we'll be able to write factorial with our interpreter. Well, what does that even mean? Well, that means we need to implement how recursion works. So we certainly aren't going to write factorial iteratively. We have to write it recursively, right? Especially since we don't have loops. But we'll add loops. Our language is going to support loops. So we're going to have to learn how do we implement if statements. Haven't done that yet, right? In order to implement if statements, what do we need to have? Boolean expressions. So we're going to have to add the Boolean type to our language. Okay, we're going to have to add conditionals. We're going to have to add loops. So all of these things that we take for granted in our modern programming languages that we kind of have the starting point for right now, but by no stretch of the imagination do we actually have a functional language that allows us to apply that stuff. So between now and the end of the semester, what we're going to be doing is taking what we have now as our stepping stone and wrapping it with the constructs that allow us to solve real problems with the language that we invented. So at some point here pretty soon, we're going to have to name our language. 2 years ago, it was the language was called Simon, named after one of our students. So we'll have to come up with a good name of the language in here. It has to be clean and certainly not named after a crappy student. All right, questions, comments, concerns.
Can we name it Pebbles and build a clock into it?
Build a clock. We'll see. Okay, so I'll stop there. If you do have any questions about your exam, line up here. I'll be happy to take a look at it and tell you why I took points off or why I didn't take points off, blah, blah, blah. Otherwise, I will see everybody on Thursday. Let me get this